Good morning, friends. Let's continue our discussion about designing of the OMS. So let's revise the problem statement again. That we are trying to build one OMS system, which is a dummy type of OMS, which is working as a TCP server, and it will be receiving the stock orders from the client on a TCP socket server. So once the order is received, there are three basic major steps which any OMS will do. It will first of all validate the order's client, then it will enrich the order with the latest market data, and then it will persist it, and then send it to the downstream. And just we have mimicked it in our in our previous videos. I've explained it that each of the request, it will take each of the steps. It will take 1 second. For example, parsing the request, then creating an order from the request, then validating, enriching, updating to the persistence, and then finally sending to the downstream. Each of these six steps, it take 1 second each. So total, it will be 6 seconds. So for the very first solution we came up with was a single-threaded OMS. That there's only one thread which would be uh, accepting the client orders from the TCP socket connection, and then the same thread would be handling that request as well. So we came up with that design. That was our design that we discussed in the first video, in which the same thread which is accepting it, it is handling it as well. So the only downside of this solution is that if there are multiple requests, say if the three requests arrive at the same time, it will take 6 plus 6 plus 6 equal to 18 seconds, because there's only one thread which is serving each of them. Then we came up with a second approach, which was thread per client request. It means that whenever any client is sending a request, the handling request, it will create a new thread to serve that client. For example, we have got this approach here. We implemented it, that the thread which is accepting the client connection, every time a client is connecting, it will create a new thread to handle it. By this way, we are making it concurrent handling of this client requests. So we also came up with this approach. By using this, if there are three requests coming at the same time, so the processing of each of them would go down from 18 seconds. In the serial threads, we were taking 18 seconds. But because now we are serving all the three clients at the same time concurrently, that's why it will be only 6 seconds for serving three clients at the same time. But we also found that there are a few caveats here. The one caveat is that there is only one thread which is handling each of the client requests. For example, this handling is done by only one thread. And in this, we have got like multiple steps like validation, enrichment, right? So this is all done in the single thread, which can be parallelized further. And the second caveat is the biggest caveat is that all these threads are platform threads, and we have learned that platform threads has got a limitation on the number of virtual cores that we have or the number of kernel threads that we have in our system. So that's why there's always a limitation that how many threads that we can create. In this scenario, if we have got hundreds and thousands of clients sending us the request at the same time, then we saw that we got an exception because we cannot create so many number of threads per request. And then we did a small optimization for the first part, that multiple threads can be doing the handling part. So this is the small optimization that we did, that instead of only one thread doing the parsing, validating, and persisting and all, there would be multiple threads doing the same thing. Again, but in that example also, we found that there's a limitation of number of platform threads that we can create, because and this is the one which we talked about. Now we have got multiple threads which can do simultaneously. They can actually parse, enrich, and validate. So in all these three approaches that we found, there has always been some limitation that how many platform threads it can create. If you're creating too many threads, definitely our system will go down. So now the solution for this is that in the fourth approach, we will see the thread pool based OMS. Before we deep dive into thread pool based OMS, let's try to understand executor and executor service, which was introduced in Java 1.5. So if I go to this diagram, this is a very basic diagram at how does executor service work. So inside executor service, there's always a task queue where we can submit the task, the runnable tasks or the future tasks, whatever. So a service will maintain a queue in which it will be having a list of tasks which are submitted to be executed. And it will always be having a thread pool. This thread pool are all the worker threads that whenever we create our executor service, there would be a fixed number of thread pools which would be available. Or in case of cache thread pool, which we will learn very soon, it can create on-demand threads. But the idea is that the threads inside this thread pool that will consume all these tasks from this task queue, and then they will execute it. Once this task is done, then the threads will return to the pool, and then it will consume other tasks in the queue. This is how the thread pool works. By this way, suppose if we have only got one thread in a single thread pool, and but still we can submit a lot of tasks at the same time. Whenever that single thread, it will keep on consuming this task and executing it, and then it will return back to consume the other tasks. By doing this, by doing such a design, is that now we have decoupled the submission of the task and the consumer or the execution of this task across the thread pools. We can submit as much as we want, based on the thread pool number of threads in the thread pool. It will consume the task and then execute it. This is very similar to producer-consumer design pattern. By having this idea, so this is way how we can control the number of threads that we can run inside an application. This will actually solve our like the previous problems, that the limitation of number of platform threads we can create. If we have got thread pool based OMS, a fixed size of thread pool, in that case we can control a limited number of threads, which will never exceed any type of limit, and it will just use that number of threads in the thread pool to service our client requests. So at a very basic level, we have got interface executor, as it was introduced in Java 1.5. It only had got one method, execute, in which it can take runnable task which we want to execute. So and a pool of thread is an instance of the executor interface, and then we have got another interface which extends this executor, called as executor service. It has got 11 more convenient methods for shutdown and termination as well. So there is one executors class, which is a utility class to create executors, and there are 20 more methods around to create the executors. Okay, so let's talk about very basic three type of executors that we can create. One is the single thread executor. It will have only one thread here in the thread pool, and we can submit a task here. But the idea is that there's only one thread in the thread pool which would be consuming this task and executing it. This can be done by executors dot single thread executor. Okay. So and as we mentioned that it's like much better advantage that now this time we don't need to create threads on demand. There would be no context switch. The threads are always there. The thread will not die and keep on creating a new thread whenever we want it. By having this executor design, this was the basic the issue which was solved by this type of design, that there are the creation of the threads and the termination of the threads. This is all not required anymore, and this can control that how many threads we want to have in our application to do our work or do our main work in our application. So besides that, there are other two ways, one as I discussed. So the second way is that we can create a fixed thread pool executor. For example, if I pass this 4, it means that in the pool there would be 4 threads which will be doing it. And then the final part is the executors dot new cached thread pool. So cached thread pool is a little bit special, because what it will do is that it will first of all take the number of virtual cores that we have. For example, if I have got 8 cores in my system, it will create a thread pool of 4 threads. But if there are so many requests being submitted, and there are more tasks than the number of threads that we have in the thread pool. In that case, it will create some new threads to consume those tasks. It will not wait like in a fixed thread pool. So it will keep on creating on demand, as mentioned. And whenever there are less number of tasks, and then we have got more number of threads than the task required, it will keep unused threads for say 60 seconds. And then by default, it will then terminate them. So it will just wait for 60 seconds. If there is no other task and any thread is like in the pool which is not doing anything, it will just terminate. So after having all this knowledge about executor and executor service, now let's design our thread pool based OMS. So it's very much similar. What we have done is that we have created a client counter as before, which will actually identify a particular client which is connected to us. It is just an increment number. So for example, client 1, client 2, client 3. This is how we are going to identify a client. Then we have got 2 thread pools. One is connection handler pool. In the previous example, as we have seen that there's only like one thread that will be in the main thread, which is accepting it, accepting the client request. Now what we have done is that we have creating a fixed thread pool of 4 threads, which would be handling this accept request. And after that, we also have for handling each of the requests, for handling each of the socket, we will be having another order handler pool in which there would be 12 threads. So again, if we compare with the previous example, there was only one thread created per client request. Now we have got a thread pool of 12 threads which will be handling this client request. So we are limiting that how many. So if there are more than 12 clients, in that case, that client has to wait. But if there are only less than 12 clients connecting at the same time, that can be all handled parallelly. So this is what this design means. So we have got two, one for collection handling and another for order handling. So let's go through the details again. Once we have got this collection handle pool, which will execute it, and then we have got handle, in which we have got multiple threads to handle it. Here it is. So here, once we execute it, now we have got multiple threads inside this 12, which are actually 12. And then we are going to validate, enrich, and persist it inside this thread pool. And then finally, we'll send it to the downstream. And then how we are going to control it, we are actually created a countdown latch. So the countdown latch works like this, is that whenever we create a countdown latch, what it does is that for each of these steps, one by one, for example, validation is one step, enrichment is one step, persistence is one step. Whenever this is done, only then we call this countdown. It means that because we have got 3, so this latch.await at this point, it will wait here at this point until all this, the latch countdown goes from 3 to 0. And this will only happen when all these independent execution tasks inside this 12 thread pool, order handle pool, that all these 3 steps will be done. Only then it will proceed from this step, from the wait. If any of the thread is waiting here, it has to wait at this point. Okay, so this is how the countdown latch works. It's very simple design. And finally, because all these 3 steps are done, validation, enrichment, and persistence, only then it will proceed from this point, and then it will send order to the downstream. So we'll see that how much time it takes. So again, just to revise it, we are going to have 4 threads for connection handling. This is where we are doing it. We are executing it and we are submitting the task like this. And once this is created, the handling part inside this, we are delegating these 3 steps: validation, enrichment, and persistence to order handle pool, which is a pool of 12 threads. And then we are actually doing a type of join type of thing from using this countdown latch, that this will await until all these 3 steps are done. And then finally, we send order to the downstream. So this is the whole design. And let's run it and see that how much performance improvement that will have. So let's run our program and see that how it works. I'll click on the run here. So as mentioned, that now there would be 4 threads would be handling the client request accept method. And then there would be another. So let's start with first 4 socket client connections. 4 socket client connections means that it will send 4 threads at the same time. And as per our design, because we have got 4 threads for connection handling and 12 thread pools for our order handling, I think it should be fine. I just run this socket line 4. And let's see that how much time it takes. I think the previous example, we were able to achieve 4 seconds of parallelism. So again, here we can see that's around 4 seconds for each of the 4 clients. Okay, so this design is good. I mean, everything is good before because we have got less number of threads now. Only like 4 simultaneous connection means that there are only like 4 threads created here in this execute every time. And this is handled well by the 12 threads in the order handle pool. Okay, so this is all good. Now let's try with, say, socket client 10,000. Okay, so socket client means that there will be 10,000 connections at the same time. It means that there will be 10,000 threads created. In the previous examples that we see, that when we are creating thread per request style, in that case, because of the limitation of platform threads, we were unable to create so many number of threads. But here right now, because we have limit the number of threads to only 4 and 12, or total 16 threads for connection and order handling, they should all work well. Although there would be a latency because after those 12 threads which have been 12 client requests which has been submitted to the task, the 13th and afterwards, it has to wait until a thread is available in the thread pool. So similarly, so that's why I mean the throughput will be affected, but still there would be no error based on the number of threads which are being created, because right now we have got limit of only 16 threads which are there in our thread pool. So let's run this for 10,000 and we'll see that how it works. So just click on 10,000. So okay, so you can see that it's all going on and I don't see any exception here. Also here we can see that because of the cap that we have, the throughput has been decreased. It will take some time, but still it is only taking 4 seconds for each of them. So this is what I wanted to communicate, that the latency part is still same. It is still going to take only 4 seconds by the number of threads we have. Right now we can run all those 10,000 simultaneously at the same time, but in the thread pool we'll see that it still keep on consuming it until we are actually the throughput has been affected, because we are still connecting or say 47, 48. So 12 each, 12 threads each time. Client's requests are served at the same time, and the other client requests has to wait until any thread is available in our thread pool. So this is, we have still reached 64, and here we have already summarized like 10,000. So you can see that how the throughput has been affected. The throughput still is gone worse, but still there is no error on the number of threads that we can create. It will eventually consume all this and then serve each of them. So this was all about this. So if we look at this, I mean the time to process a request is still same. It will take 1+1 for order and all. So let's go here again. It's still working here, so I'll just put it down. So again, the first two part, 1 second each, so it will take 1+1 2 seconds. Now we are using countdown latch, and then we are running all this validation, enrichment, and persistence in 3 parallel threads. So it would be max 1 second each again, because this is all done in concurrency, and then finally send to downstream 4 seconds. So here it is going to take 1+1 plus max of this 4 seconds. Again, there are few caveats here in this design. Although there's no error that we can see now, we can have multiple clients connecting at the same time, but of course the throughput has been decreased because of the thread pool limitation. Another is that order is a shared object amongst all the threads and needs to be synchronized. This is what we have also learned in our thread pool design. Whenever we are trying to handle the socket client request among the multiple threads, we have to synchronize the order and all its methods like validation, enrichment, precision, and all. And now code is more complex because we are also using helper objects for using that for joining those threads once we parallelly serve it in the pool. So far, what we are seeing that we are designing all these approaches. For example, all these like 4 approaches that we have done. These are like very imperative style. So threads do the things, they act on a shared object and then modify it, and then finally send to the downstream. Now in the next video, we'll see the better design, which is based on the future based. So we will use asynchronous programming now. So from here onwards, instead of using the imperative style, we are going to use asynchronous style of programming, and we will further have the next approach of using futures for our OMS. See you all in the next video.